Hello and welcome. We are going to start the third day session on thermodynamics. And this live program is being streamed in Facebook for the third time. And I am observing that the streaming is good because I was trying to watch every video. I used to record also in my system. I find that recording, the streaming, the flow is consistent with Facebook. So it is definitely a good streaming service platform. So anybody have joined me live can have a chat with me to make sure that we are in the right track. Am I audible? Voice? Anybody? So in the video that some of you might be watching, you just scroll for a few minutes, because in the first few minutes I used to make sure that things are going on, my audio is visible, I mean my voice is audible, my video is visible. So unless that is being ensured, not possible to start, because that will be futile. Oh, so how can I go to my page? I'm not able to see my chat box. That is why I am not able to. This is very difficult. Chat box. Once I go to, where can I get? Happening now. Okay, but where is? Hello. Hello. Happening now. Okay. Anyone who is watching now can write a little message. Yes, then I can see somewhere. I am not finding the message box. That box is vanished from my sight. So I am now lost. I am unable to revive the page where I can see the very complicated. If I cannot see who is watching, who is not, there is no point in having this program. So I have to close the program and reschedule later. Sorry for the inconvenience if someone of you is watching. Please bear with me that today I could not link properly to the Facebook. I'm not able to see anyone or even the chat box. Where is the chat box? I'm trying to open, but it is not opening. Where to also end event, that also I am not able to find. Where is the end program? Where to end? Where to end? Steve, are you there? Good morning. Steve, are you there? Now I will be able to. Where to end? Steve, are you there still? Just write down, yes, I can now see. Sivdat, are you still watching? Yes, I am able to see now. Are you still watching? I have not yet cancelled. Just write in comment box that you are watching, so that we will start. Never mind if it is maybe 15 minutes late, we don't mind if we are really interested. Okay, I get the signal that Sivdat is there, and we will be starting our program as passionately as we did for the last 2 days. There is a famous saying, there is a famous saying in Odia, which sometimes I use while teaching, that not Odia, in Sanskrit, that ekas chandras tamohanti nachatara ganirapi. One moon is enough to eradicate, to dispel the darkness of night. Yesterday was here, almost a full moon day. We were watching, although in our conventional religion, we are prevented to watch the eclipse time, either the sun or the moon. But we don't have any reason why not to watch. So we watched how the moon is being eclipsed, eaten away by a monster that we used to listen in our young days, and then the monster leaves, then again becomes totally dark, and then again slowly it comes out. So ekas chandras tamohanti nachatara ganirapi. Stars are thousands and thousands and innumerable, incountable, uncountable. They together cannot dispel the darkness. So if only one student is staying live, let me tell you honestly, staying live to watch my program, then that is good enough for me. For a person like me at 70, studying every day and trying to update every day, helping students disseminating my experience. That is enough if one guy is interested or many guys are interested. Today, many have written to me that they will not be available for some important work. They will be watching later. But let's see that we start. Have you watched the last part of the numerical that we had yesterday, where we compared the reversible adiabatic expansion, where the decrease in temperature is more, the final temperature is lower, 207 we calculated, and we use the adiabatic gas laws, which are applicable only for reversible process, not for irreversible process. And but for irreversible expansion or compression adiabatically, we have N CV delta T is used for both, but the delta T are different. There lies the trick. Then what we do for irreversible, we equate P external minus P external delta V is equal to N CV delta T. So from this we find the temperature. Only T2 final temperature is unknown in left side. Final temperature is also unknown in the right side. So we yesterday found the temperature was 287 or something, much greater than when we found the temperature, final temperature in adiabatic reversible expansion by using the adiabatic laws. In that, yesterday we used T1, T2 by T1 to the power Cp is equal to P2 by P1 to the power R, that we used and got the final temperature was 207. And in compression, it is the opposite. More heat will be produced in adiabatic compression than irreversible process is a big rectangle than the reversible compression. So in that case, temperature increase, the final temperature in irreversible compression is more than the reversible compression. So have you seen? Once again, please write down, Shivdat will be doing. And the moment your data pack will be going to be over, you just tell me so that we will close and we will begin the rest tomorrow. So since we are already late, are you listening? Once again, right? I'll see the chat box moving. Yes, Sibdat? What you are supposed to write? Yes, sir, it's okay. But have you gone through those last portion which you missed? Or shall we solve a problem again? Similar type of problem again. Hello, Siv. So I am not able to distinguish between multiple yes sir. So will we solve similar problem again? You write if yes, write solve sir. If no, no sir. That means solving such type of problem is not required. You understood how to tackle it. Say no sir. Oh yes sir, I have seen the numerical. Okay. Now we are going to a different scene where we will be coming deactivate. Okay, and we'll be taking our we'll go to another page, and without yes. So let's start. So far, what we have studied, the important relationship that we had built up so far is from final to backwards. I'm saying that work done in a reversible isothermal is minus 2.303 nRT log V2 by V1 or P1 by P2. And work done in any reversible process, may it be adiabatic, may it be isothermal, minus P external into del V. We have seen also n Cv delta T is equal to del U, n Cp delta T is equal to del H. Then while introducing enthalpy, we knew del H is equal to del U plus P del V. And for chemical processes, del U plus NR is a delta nRT, chemical reaction. And for other processes like isobaric, isochoirc, where there is a change in temperature, you have this is equal to NR delta T. For isochoirc and isobaric processes. In also adiabatic, there is a temperature change in all the processes, adiabatic, isochoirc and isobaric. And also we knew in free expansion, everything is zero. Work is zero, and if it is isothermal, del U is zero, Q is zero, and if it is adiabatic, Q is zero, del U zero, everything comes to zero. But what will be non-zero, I will tell you while we enter into thermodynamics. The entropy change will not be non-zero if it is done fast. And what else we knew yesterday? We cyclic process, going from same point to coming back to the same point, maybe by 2 steps or maybe 3 steps, 4 steps. Then it will be isothermal and cyclic, they are similar. Del U is equal to 0, and whatever work will be done, it will be at the expense of the heat exchange. And for that del H is also 0, both. And we have seen for isobaric process, we have already adiabatic, there is also del H. Del H has a significant meaning, which is equal to del U plus V del P. I'm sorry, this is for isochoirc, where volume is fixed. So for everything, del H is equal to del U plus NR delta T. But to express it in a different way, isochoirc, del U plus V del P. But for adiabatic, it is del H is equal to del U plus P2 V2 minus P1 V1. For microscopic change, for a differential small infinitesimal change, it is dH is equal to du plus P dV plus V dP. But for a bulk change, large change, it is P2 V2 minus P1 V1. But anyway, del H is equal to del U plus NR delta T. Temperature is changing, so why not we use that? So with this revision, let me tell you what is the meaning of, now I reveal, irreversible chemical process, chemical reaction, where our unique interpretation in chemical science, chemical thermodynamics will set in. Is irreversible doesn't mean that it is a fast process. Even in expansion compression, irreversible never meant that you cannot reverse. It meant only fast. Simply fast process. Natural processes are very fast because they work on a large gradient of anything. May it be temperature gradient, then it is heat flow, or any other gradient, it is work flow. So that is a very fast process. That's it. You can reverse. In irreversible process, ironically, you can reverse the process. But you have to leave some permanent changes in the universe. Either the entropy of the system will increase or the entropy of the surrounding will increase. So the net entropy of the universe has to increase. That is the beauty of second law that we will study today. So in chemical system, it means it is a right or product favored reaction. So that the equilibrium constant is 1. The more it is irreversible, you cannot easily do the reverse reaction. So silver nitrate plus NaCl giving precipitate, silver chloride, white precipitate and NaCl. That is the equilibrium constant is 10 to the power say 10 to the plus 10 or plus 20. So if such is the irreversibility, then you cannot get back silver nitrate and sodium chloride by adding silver chloride and sodium nitrate. The reverse reaction is almost impossible. More it is on the right side, less is the possibility of the backward reaction. See the difference. It is not fast. Nothing to do with speed, fast, slow, no meaning in chemical science. And reversible means not slow, is it will attain equilibrium at certain stage. And it is not very much right favored, but at some point it will come to equilibrium at certain stage. And we have another term for this, it is spontaneous. We use the term spontaneous in both, also in chemical, which is right favored, goes towards almost completion, and in reversible, it doesn't complete, it remains somewhere in the middle. But there is another term, non-spontaneous, which I add in addition to reversible, I add non-spontaneous, where it is left favored, left or reactant favored. Either the reaction is not happening, if happening is very to a small extent, equilibrium constant is very much less than 1. So here we say equilibrium constant is exactly 1. We say that doesn't mean that the product amount and reactant amount will be exactly equal. There can be any amount, but somewhere it will come to the equilibrium. But this will be less than 1. As we shall see, study the second law, we shall apply, and then we will see why this is called. So there is a famous saying in chemical thermodynamics. There is a famous saying which the physics people perhaps will be very difficult for them to accept. They will have to accept. The term is, see, if thermodynamics says no, it means no. It means no. the reaction will not happen, it will not happen. But if thermodynamics say write down what I'm writing. Thermodynamics say yes, it means it may be, or it may not be also. It may be. That is the saying it may be. If thermodynamics say no, means no. If the equilibrium constant is what? If you are a beginner, you have not studied equilibrium, supposing AB gives C plus D, and equilibrium constant is nothing but the product concentration multiplication of the product concentrations, molarities, and divided by the product of the concentrations of the reactants. Of course, when there is a coefficient, this will appear as power. So from equilibrium constant, you have a knowledge about to what extent the reaction has proceeded. If the equilibrium constant is more than 1, more than 1, then it is going inching towards the product side, more and more to the product side. If it is 10 to the 10, it is almost complete. 10 to the 5, almost. But if it is less than 1, then it is to the left side of the midpoint. The midpoint, equilibrium constant is 1. So this ratio is 1. That doesn't mean that reactant and product will be exactly same. That depends on how much reactant you have started with. So the equilibrium constant is 1. Okay. But if it is less than 1, then reactant concentration is more. Product concentration is less. But the reaction has halted. Of course, dynamically halted. So, and supposing it is 10 to the minus 5, then almost the reaction doesn't happen. 10 to the minus 5, equilibrium constant, all are less than 1. 10 to the minus 10 also is less than 1, not less than 0. They are not negative values. They are less than 1. So, from the equilibrium constant, you can have a knowledge, ये reaction का नतीजा क्या होगा, भाग्य क्या है, ये जाएगा, अगर कुछ तो जाएगा, हो जाएगा, हमारा काम हो जाएगा तो ठीक है, अगर नहीं है तो कुछ करो ना. So you will be surprised to know that N2 plus 3H2 giving 2 ammonia, all gases, the equilibrium constant at 298 K, that is the room temperature, is of the order of K equilibrium is order of 10 to the plus 5. So equilibrium, thermodynamics, these are all from thermodynamics, we shall study. Say yes. But the reaction doesn't happen. Does not happen at room temperature at all. Who is the villain? In chemistry, the villain is kinetics. The rate of reaction is so slow at room temperature, even at 200 degrees Celsius, 300 degrees Celsius, the reaction is so slow. This is called the kinetics of the reaction is so slow that even if the driving force is there to go to almost to the product side with equilibrium constant 10 to the power plus 5, but it doesn't go. Therefore, our slogan is, if thermodynamics say yes, it doesn't mean really always yes. It can be yes. In some cases, the reaction rate is even fast at room temperature. But in many cases, the reaction rate is governed by temperature and only temperature. So, at some reactions at room temperature, the rate is almost 0. So, क्या होगा? आपके पास आपका कोई दोस्त, कोई गेस्ट आपके लिए इतने सारे मिठाई लाए हैं, लेकिन आपका unfortunately, I'm just not saying anybody, somebody like me, supposing I have a huge diabetes. So क्या होगा? ये इतना सारे मिठाइयां घर में है, लेकिन मैं खा नहीं पाऊंगा, मर जाऊंगा. तो इसलिए yes, there is a driving force. Yes, but if you raise the temperature again equilibrium constant will decrease. That is, again, equilibrium constant is also dependent on temperature. So equilibrium constant will decrease. So even then we have to make a compromise. Low temperature mein equilibrium constant is high, but reaction rate is so slow, it is not happening. Then say above 500 degrees Celsius, the equilibrium constant becomes so low that the product amount will be scanty, even if the rate will be faster. But we have to make a compromise. That compromise is called the optimization of temperature. So in any industrial process, ammonia has to be prepared by this method, Haber's method. Nitrogen is abundantly available in nature, in air. Hydrogen we have to prepare by electrolysis. So we have to get ammonia by this. हमारा भाग्य ESC में है that we have to do. K equilibrium has gone low. At 500 above it becomes very low. But even then we have to adopt. At 500 degrees Celsius it comes to 10 to the minus 5. Even then we have to compromise and get, even if a small quantity, but continuously you will be studying chemical equilibrium, continuously drive the product away from the vessel so that the equilibrium will be shifted more and more towards the right, and we trick the reaction and get completion. But you have to go to the optimum temperature, not high, not low. So therefore, but when the equilibrium constant is low at a certain temperature, supposing had it been at room temperature, had it been 10 to the minus 5, then nothing can be done. You cannot change the equilibrium constant at a particular temperature. So nothing can be done. But if it is yes, thermodynamics saying yes, you cannot give a guarantee that the reaction will happen. You have to look to the villain, kinetics, what it says. Will it allow it to happen? If yes, it will. Okay. With this, let us go to the second law. Second law was produced, was put forth for, see, because first law was not adequate to solve, to explain things, why many reactions which are endothermic. Actually, people had a belief that only exothermic reaction are spontaneous, irreversible. That means del H is negative. These are called exothermic reaction. HP minus HR, the enthalpy of the product minus, so this is del H, is negative for exothermic. They were thinking that as if only exothermic reactions where the energy falls down from the original value, from the starting value, then that goes spontaneously. But they found many endothermic processes. HP, P means product. And this is the transition state, the extra amount of energy that has to collect from the surrounding, that is called the activation energy. That is the case for every chemical reaction. It has to be activated, ready for the collision, bombardment, breaking of the bond, and then they fall down to the product side. Finally, this is the amount which is required, observed. So in this case, del H is positive, and this is endothermic. So people were thinking endothermic reactions are non-spontaneous. Exothermic reactions are spontaneous, but they found umpteen number of endothermic reactions are stable. For example, melting of ice is spontaneous at room temperature, or anything above 0 degree. But it is endothermic. It is absorbing, molar heat of fusion or latent heat of fusion amount of energy to break down the hydrogen bonds and other things, so that it will change to the liquid phase without change in temperature. Only the energy is used for, breaking the potential, increasing the potential energy, not the kinetic motion. So unless there is increase in the kinetic motion, kinetic energy, potential energy, speed of the molecules with which they are vibrating or translation going on, moving from one place to the other, then U is not going to change. U is not changing means temperature is not changing. But the energy is being invested by doing some potential, breaking some potential energy and then breaking hydrogen bonds and all that. So similarly, if you or sodium nitrate or potassium nitrate, you dissolve. These are solids. Dissolve. They dissolve endothermically. This requires some energy plus delta endothermically. But it is spontaneous when you add sodium chloride, namak, पानी में डालो, थोड़ा सा stir करो. It will automatically, you are not needing to hike the temperature, to increase the temperature for dissolving sodium nitrate, potassium nitrate or whatever salt. Most of the salts dissolve endothermically but spontaneously. No temperature increase is required at room temperature. So then people want several such reactions happen. They found not only the phase transition like melting of ice, boiling of water, they are occurring endothermically but spontaneously. Water boils at 100 degrees Celsius spontaneously. Water above 100 degrees Celsius spontaneously. 100 degrees Celsius it boils but remains at equilibrium between the liquid phase and solid phase. Vapor phase and liquid phase. And ice melts spontaneously above 0 degrees Celsius. At 0 degree, it remains at equilibrium. And the equilibrium constant is 1. As I have told you, that remain in equilibrium. Doesn't matter whether it's 50% ice or 50% water, doesn't matter. Because you will know that pure liquids and pure solids have activity 1. It's not a solution. Pure ice will be in equilibrium with liquid water. So the activity 1. So equilibrium constant 1 means activity is 1. But the amount may be whatever, but they will remain at equilibrium. So a new term was introduced. I'll tell you how it was introduced later, but introduced, that is called entropy. They thought for spontaneity, the entropy change delta S. I will introduce entropy in an isolated system. Or universe. Supposing you are doing in a closed system or open system, we have to take the universe because there is a heat exchange, work exchange that can happen. But in adiabatic insulated, it is only work exchange can be done, but heat exchange cannot be done. So if you are taking isolated system, okay. Not a non-isolated system, then universe. That means system and surrounding. Either doesn't change, एंट्रोपी चेंज हम नहीं लिखेंगे. एंट्रोपी ऑफ द यूनिवर्स, द net entropy of the universe. Net entropy in an isolated system or universe either remains same or increases. In a spontaneous irreversible or natural process can never decrease. So there is another thermodynamic state function was introduced called entropy. So del S either can be equal to 0, change. It remains same means final state minus initial state will be 0. Or increase means final state minus initial state will be greater than 0, positive. So for any spontaneous process, it will happen, possible process. So this you have to write universe. This is very important, universe. So this is called Clausius Inequality theorem for second law. Second law has been defined in several ways. This is the Clausius inequality for second law. Del S, a universe has to be greater than 0. Then what is entropy? Entropy is a measure of chaos. In a system. Measure of disorder, how much the molecules inside the system are chaotic. They are disorder. More the disorder, more the entropy. When you are sitting, you are meditating, your entropy is less. When you are walking, dancing, your chaotic motion is going on more and more, then your entropy is increasing. So to define mathematically, the small change in entropy is equal to the heat absorbed at a fixed temperature. Remember, that was del T for heat capacity. This del, D per unit, but this is fixed temperature. At fixed temperature, whatever Q it will take, that by the temperature is the entropy change. In reversible manner or irreversible manner, this will be reversible or irreversible. So if you change from initial state to the final state, if you make a integration, this will be del Q. From the initial state to the final state. But I am not saying T1 to T2. T is remaining same, but you are sending heat or removing heat reversibly in a slow manner for some time. The total is, say, Q. We don't write delta Q because this is an inexact differential. So the total heat absorbed revolved by the fixed temperature. This reversible heat absorbed or evolved by fixed temperature. That is del S, S1 to S2. So the entropy change that occurs at a fixed temperature is equal to the heat absorbed or evolved at the same temperature divided by the temperature. So the unit will be little different. It will be joules per Kelvin or calories per Kelvin. The unit of entropy. Entropy is a state function. The unit will be joules per Kelvin or calories per Kelvin. Sometimes we make it specific, intensive, molar entropy change or molar entropy. That can be joules per Kelvin per mole, and that is an intensive property. State function, but intensive. But this S is extensive. But if you specify 1 mole, 1 kg, then it will be intensive. So internal energy can be intensive, that is called specific internal energy. Volume can be intensive, specific volume. Entropy can be specific, molar entropy. Can be intensive. Now, interestingly, while enthalpy and internal energy of a system, absolute internal energy, absolute enthalpy cannot be determined, can never ever be determined. Their changes are determined from a calorimeter, but absolute entropies are determined from third law. We shall study third law. We shall know how we can determine the absolute entropy of a particular system at a particular temperature, starting from 0 Kelvin, minus 273 degrees Celsius. We start and come to, you apply the physics principle, the heat principles. From this to this, delta T. In liquid and solid, we have only Cp, delta T. And when phase transition occurs, then heat of fusion. Then again, from this to that, Cp delta T. And when again vapor comes, that is heat of vaporization. And then from the vapor state, from that to that, again there is, but there you have a choice whether you are to take Cp or CV. In gaseous phase, you have two heat capacities. Heat capacity at constant pressure and at constant volume, they are different. Cp is more than Cv by an amount equal to R, which we have done extensively in our last 2 days program. Now, so we know del S universe should be equal to 0 or greater than 0 for any possible process. I say possible process. If it is less than, this is second law, the first introduction of second law, but that will be manifested in different ways. So del S universe, if it is less than 0, it is an impossible process. I used to say, ये नहीं होगा. Now see this interesting case. If Q is constant, same amount of, supposing you add 5 joules to a mole of 18 gram of ice, which is at 0 degrees Celsius, and you add same 5 joule to 100 degrees Celsius vapor, water vapor, 1 mole of water vapor. Since del S is inversely proportional to T for fixed amount of Q, then it will change a greater entropy increase in ice, which is at a lower temperature, than water vapor, steam, which is at a much higher temperature. If this is more, this is less. Just like you go to a big auditorium where the entire auditorium is jam-packed and you are sitting somewhere, and supposing you sneezed, so nobody can, you cannot also hear your own chink. But supposing you imagine the entire auditorium is vacant, nobody is there. You are sneezing inside it. There will be so much of chaos. The chaos, the increase in entropy will be enormously large when the same sneezing chink you are doing in a crowded hall where, I make an analogy with temperature. High temperature, you add same heat. Low temperature, you add same heat, but the entropy increase will be more in low temperature condition if Q remains same. Obviously, when T remains same, then more the heat, more the entropy change. That is any XYZ era, Tom, Dick, Harry can answer. But this is very important to note. And the chaos, the disorder, इसलिए मैं I tell to students often, funnily, that you do all mischief. You in your room, I'm showing this slide. See, this girl was given a single room by her parents. So the mom made this in a perfect order. But after a few days, mommy discovered that the girl has made a mess, scattered. So the entropy of this house is so low and this is so high. The chaos, the disorder is so high. But thermodynamics says spontaneously the entropy of the universe, but not system alone. But since mommy is ordered outside, mommy's daddy is supposing outside, they are surrounding. And this girl with a room is system. So she is increasing the entropy. So then she will come, when mommy will mad at her, will be angry. Say, what had happened? I made so ordered all the things and you have done it a mess. Mommy, second law thermodynamics perhaps you have not studied. The second law says that entropy of a natural process, of a possible process, irreversible process always increases. Since you are ordered, they are outside being surrounding, I have to become disordered. So my entropy has increased. So it's natural. Then mommy will be fooled. Are you listening, Siddharth? And you write to me when your data pack will be over, so that we can. Anyone watching? Siddharth, are you watching? Shiv. Shiv. Yes, sir. Okay. There is a lag, a few seconds lag. Now, what you are doing, let us try to understand the very important thing. When del S is positive, in which cases increase in entropy occurs? When solid melts into liquid at melting point, the liquid, the molecules are at greater freedom to move. So the entropy increases. More is the motion, more is the mobility, the entropy increases. And when liquid changes to vapor, then also there is a large increase in entropy. So in these cases, del S is positive. Increase means final minus initial is positive. And the reverse is negative. There is a decrease in entropy. Now, another is increase in volume or decrease in pressure. Same thing of a gas or fixed mass. Supposing you have a gas of fixed mass, you raise the piston so that the volume increased and pressure dropped, so that the molecules will have a greater access to more space and their chaotic motion will be more, the disorder will be more. But you do the opposite, you compress, the molecules will come from a more disorderly state to a more orderly state. So entropy will decrease means del S is negative. And in some reactions like ZnS plus HCl, AC, gives you ZnCl2 AC plus H2G. So once there is a gaseous component, you have to find out the number of change in the number of moles. Solid and liquid, they in the phase of gas, they do not contribute much to the entropy. So the change in entropy is highly positive when the number of gaseous moles in the right side is more than the left side. Even when we decompose ammonia, the other way around, we don't do that. Ammonia formation is more important. We are doing in a very unfavorable condition, 10 to the minus 5, फिर भी हम करते हैं optimize करके temperature हम करते हैं. Thermodynamics say yes means it doesn't mean yes, it can be no. So we cannot do it in room temperature even at 200 degrees Celsius. The rate is so low. So this 3 plus 1, all G. So this is del S is positive because more number of moles are produced. 4 moles are produced from 2 moles. And therefore, the system has to increase its chaos, disorder, and hence even if you go from a simple compare between simple to more complex, entropy increases. Compare. This is for comparison. More the molecular mass with molecular mass and complexity. Molecular mass may be same, argon, 18. So 18 is closer to methane. So methane has a greater complexity. Molecular mass remaining same if it is a monoatomic and there is a diatomic, triatomic, then complexity agar badhega, to their vibration, their rotation, there will be more, the chaos will be more, entropy will be more. And another is increasing mass. in fixed volume. Supposing you have added something more, volume is fixed. So automatically pressure will be more if you're adding some more mass, and there will be more bombardment, more chaos inside. Adding some more mass will definitely increase the chaos. But if the mass is constant, they are at a smaller volume, then they are in orderly state. I mean, disorder is less, entropy is less. If you expand it, then entropy will be more. Del S is positive. So the opposite is del S negative case. You must remember that's the opposite. Like formation of ammonia, all gas, the number of moles is reduced. A vapor converting to liquid, converting to solid. So you can know what processes will be involved in del S positive and which involve del S negative. Of all physical and chemical processes you can know. Then coming to prove that why melting of ice is spontaneous at say 25 degrees Celsius or even 1 degree Celsius, anything up. Let us see, supposing it absorbs the molar heat of fusion. So the increase in entropy del S system is equal to Q by system is melting at 0 degrees Celsius. System has 0 degrees Celsius. The environment, the surrounding is more than 0. So this is Q by 273. So that is positive. Yes, Q is positive here. It is absorbing. The surrounding is at a different temperature. Q minus Q. This is minus Q. It is losing by 273 plus something. Say 25. It is minus Q by 298. So if you add up system plus del S surrounding, which is equal to del S universe, will be equal to Q by 273 minus Q by 298. So loss agunele 298 एठी चली आसीबो, एठी चली आसीबो. Q टा same अछि. So this will be positive. If you take LCM, then 298 will come and the result will be positive, and hence it is spontaneous. Therefore, scientists could find a reason why. They said for any spontaneous process, the entropy, the disorder, the chaos of the universe means system and surrounding together. They interact together. If it is isolated, then inside only that insulated system. If it is not, then the surrounding कायनात उनको मदद करने चला आएगा. कायनात, I mean surrounding. And why it is exactly in equilibrium at 0 degree? If this is 0 and that is 0, then this will cancel out. Del S will be equal to 0. In that case, they will remain at equilibrium. Both ice and liquid water will remain. If you keep the thermostat at 0 degree, then jab tak rahega chand aur suraj, ice or water will remain at equilibrium. But that never happens because we don't keep it inside a thermostat which is maintained at 0 degree. We keep it open or something at a higher temperature than, but at 0, less than 0 in deep freeze and fridge, then this becomes, the opposite. The surrounding, this will be minus something, 270 minus, supposing 5 degree, minus 5 degree surrounding mein hai. So this 298 becomes 270 or 270 or 260 surrounding का. लेकिन आइस तो मेल्ट करेगा 273. आइस में आइस इज 273. इसका अंदर तुम हाथ डालो और घुसाओ एक थर्मोमीटर, आपको 273 मिलेगा. लेकिन बाहर का एनवायरनमेंट इज -5, -10. सो ये अगर 270 हो जाएगा और 269 हो जाएगा, so this becomes negative. That is why ice will never melt in a deep freeze or in a freeze where temperature is 0 degree, below 0 degree. So they could find the explanation for all processes which are happening, which are possible, taking place spontaneously at a given temperature. They could explain even the endothermic processes like melting of ice or any I told you, no, that sodium chloride deserves, that is the difficulty in sitting with me. Because from something I will drag you to some other thing. And people like Shiv, they relish. That's why I get the impetus, the encouragement to speak something different from what is going on. So sodium chloride solid AC gives you sodium plus AC plus Cl minus AC, dissolution simply. And this is endothermic. So this delta H is undoubtedly positive, I told you. Why? Because this is a sum of the heat of the lattice enthalpy which is positive, but to break the lattice, and hydration enthalpy which is released, this is negative, this is positive. You have to break the lattice into ions, gaseous ions, and then ions will be solvated. They will be surrounded by, each ion will be surrounded by water. By that, energy will be evolved. That is called heat of hydration. So even if it is negative, this is positive. The sum total is positive. That is why we say del H is positive. This is heat of solution, which is a mixture of, which is a sum of lattice enthalpy and hydration enthalpy. So what happens that the reaction becomes spontaneous? That we shall know after a bit. After a little bit now, we shall be studying the same second law in terms of free energy change. So del G naught is equal to del H minus T del S. So this is positive, no doubt. Now entropy change will be replaced by free energy change to make the definition of second law more accessible, more applicable, because in this form of second law, we are completely eliminated the use of surrounding in the equation. Surrounding does play a role. This del G0 system, these are all system. Nothing is system. So everything is precipitated, is coming down to system. So it is easier to measure things inside the system than to monitor what is going on in the surrounding. So this term will come after some time. And just like we learnt that del S universe should be positive or zero for a possible process. In the similar way, we shall study del G system. Del G system should be negative, just the opposite. Should be negative, less than zero for a possible, or zero is equal to zero, equilibrium, midpoint equilibrium, and greater than zero, positive, impossible. Just the opposite of entropy change of the universe, but it is a system. So see, even if this is positive, there is a minus sign here in this equation. This is the famous, the Gibbs equation or Gibbs-Helmholtz equation. We shall be doing. I am giving you fantastic, much improvised and modified notes extensively. You can look to the, if I am forgetting to send you personally, you can go to the Facebook, my page, Sudhanshu Tripathi, and I'm always uploading because Facebook is unable to store. There is a very good streaming platform. I congratulate Facebook. If Facebook you are watching me, I congratulate you. But since your network is larger, perhaps than any platform, therefore you cannot keep longer videos, right? So no ways. You are friend to YouTube. So YouTube is doing this marvelous work. We are also sharing this video, uploading this video. For that we have to record it. I am recording. Yes, its recording is going on. So what happens, Shiv? Del S becomes enormously large because when melting of ice will occur, solid to liquid, then the entropy change is highly positive. So T del S is highly positive and the magnitude of T del S becomes more than the magnitude of positive del H. So the net result minus sign is there, is negative. So when del G system becomes negative, then it indicates that it is a spontaneous process. So it is happening because of the entropy factor. The entropy factor is, of course, here there is no mention or any use of surrounding entropy that is being embedded here inside. But surrounding plays a very important role in making a process spontaneous. Even if it appears from the enthalpy change that it is requiring more heat than the reactant value, but that extra heat which is demanding appears to be an impossible process. That makes that is made possible due to the contribution of T del S factor, this entropic heat factor that is possible. Right? I will tell you more and more about this. Before that, let me see. Oh, well, let us try to find out del S, entropy change for different processes. Now, let us start from this first law. dq, and of course, del q is equal to du plus pdv. I am following my chemical convention. Du, the bank balance, is equal to q plus w. Plus w is equal to minus pdv. So it has become plus here because we have started following physics, keeping q, but we have not started saying that w is negative for expansion, compression, and negative for expansion. Expansion is negative, we say, they say positive. Compression, we say positive, they say negative, which Shiv is unable to reconcile. Why? So let us start from here. Okay, be careful. Now let us do something. This is equal to CV N, number of moles is N, Cv is molar heat capacity, NCV dt. We already know du is equal to NCV dt. Plus, in place of P, let us write nRT by V dV. So then let us divide by temperature. So dq by fixed temperature T is equal to NCV dt by T. And here T is getting cancelled. nR dV by V. So now we can integrate for the whole temperature range. Because although entropy at a fixed temperature is Q by T, but if you supposing you raise the temperature from T1 to T2, then all these will be added up, the area bound by the curve of Q by T. So that is the integration. So here we get del S. Here we get del S. This is, let me do one more step. So this is ds integration from initial state to final state, and this is NCV. This is nothing but ln T2 by T1, taking T1 to T2, T final to T initial. I will take T initial as T1 and T final as T2. So T2 by T1, and plus nR ln V2 by V1. When V1 is the initial volume, V2 is the final volume. I think you are not able to see. I am raising it up. You can see. I had promised not to go. I will not cross the Lakshman Rekha, but I am crossing again and again. Rituparna has come back. Okay. Hello? Sorry. So this is integration ds is del S, change in entropy. That can be positive, can be negative. This is n Cv ln T2 by T1 plus nR ln V2 by V1. So two terms are needed. Temperature, volume, or you can, if you want pressure change, then there is another way which we will not spend more time using PV is equal to nRT equation of both the final state and initial state. In my notes, you will find the derivation. It will be minus nr ln. Oh, this will be Cp. I'm so sorry. This will be Cp. If you bring in pressure, then it becomes, the first one will be Cp, then nr ln P2 by P1. Same, T2 by T1, P2 by P1, but there is a minus sign. So these are the two fundamental equations to find entropy change for any process. So the derivation, how this became this and this change Cv to Cp, that you will find, I will show you in my slide. But so whether it is, supposing we take isothermal. So the T constant, this term will be ln 0 is equal to 0. Oh, by the way, for solving problem, you have to make 2.303 nr log V2 by V1. I am not writing. You understand. Let me not disfigure it. We shall be solving problems after some time. So here also 2.303, here also 2.303. Same thing here. For isothermal case, then this becomes ln 1 is 0. Temperature is same. So this term vanishes. So del S becomes reduced to nr ln V2 by V1. And in this term vanishes, so it becomes minus, make it plus, it becomes plus nr ln P1 by P2. So this is same thing you would have got had you started that del S is equal to Q by T. Q is equal to minus W, because in isothermal Q is equal to minus W by T. And the work is itself minus 2.303 or nr T log V2 by V1 or P1 by P2. So by T, so T gets cancelled, so that you get the same thing as you have got now. So plus nr. So T get cancelled, nr ln V2 by V1, or the other equation gave us plus nr ln P1 by P2. So whether you get from this main equation or individually apply the condition for isothermal change Q by T, you will get the same thing. But I prefer this one, you remember. Del S is equal to what? Okay. Del S is equal to NCV ln T2 by T1 plus nr ln V2 by V1. And you must remember also, if no volume data is given, pressure data is given, then you have to use Cp. And Cp ln T2 by T1 minus nr ln P2 by P1. But for solving problems, you have to make 2.303 log. And similarly, we can use to isobaric process. So isobaric process, we shall be taking this one, pressure remains constant, this one, where pressure remains constant. This term will vanish, so it will be simply del S entropy change will be equal to nr ln Ncp ln T2 by T1. And applying Charles' law, you can write Ncp ln V2 by V1. Because Charles' law is applicable here. Thermodynamics law was applicable. Ncp, T2 by T1, V2 by V1. Similarly, in isochoirc process, there is also a temperature change. There is a temperature change and hence entropy change. Isochoirc. tell me one thing. In the original definition of entropy change, small del Q is equal to del S. ds is equal to del Q by T. But T was in the denominator. It appears that when T increases, the del S becomes less and less. So that is not to be utilized here. You are going from temperature T1 to temperature T2, 200 to 400. Supposing you are carrying out an isobaric process where you are increasing the temperature, you are increasing the volume by changing temperature. So T2 by T1, T2 is more, T1 is less. Therefore, del S is positive. टेम्परेचर बढ़ता है तो एंट्रोपी बढ़ता है, वॉल्यूम भी बढ़ता है. यू कैन ऑल्सो डू दिस वन. वॉल्यूम बढ़ेगा, ये भी बढ़ेगा. टेम्परेचर अगर बढ़ेगा, एंट्रोपी बढ़ेगा. देयर वी वर डूइंग एट अ फिक्स्ड टेम्परेचर, बट हियर वी आर इंटीग्रेटिंग फ्रॉम T1 टू T2. तो अगर टेम्परेचर बढ़ेगा तो एंट्रोपी बढ़ेगा. T2 इज इन द न्यूमरेटर, V2 इज इन द न्यूमरेटर. तो वॉल्यूम बढ़ेगा तो भी एंट्रोपी बढ़ेगा. लेकिन दोनों टर्म अगर आपस में हेल्प करेंगे, T2 by T1, this is positive and this is also positive, so सोने पे सुहागा. But since in isobaric process the pressure is remaining same, so you have to do this 0, and once it becomes ln T2 by T1, it should be V2 by V1, but Cp will be there, not Cp will be there. Cp V2, here there is nr ln V2 by V1, but that will be n Cp ln V2 by V1. Charles' law. What do you find here? We'll be solving problems. In isochoirc, this term, you take this, volume will be 0. Again, we take the first one, as we took for isothermal, removing this. For isochoirc, we will remove this and keep only del S isochoirc is equal to n Cv ln T2 by T1. And applying Amonton's law, same n Cv ln P2 by P1. And for adiabatic, it is very interesting. Adiabatic, let me write down both the terms again. N Cv ln T2 by T1, which we derived, plus nr ln V2 by V1. And alternative one is n Cp ln T2 by T1 minus nr ln P2 by P1. These two equations are fundamental for any process. But remember, in adiabatic, in case of reversible adiabatic, expansion हो या compression हो, del S will be equal to 0. When I say del S, I mean system. Because this term, see the irony. Temperature decreases in expansion, temperature decreases. T2 is less, T1 is more. Volume is more, volume is less. So one term is positive, volume term, and the temperature term is negative. So exactly if you do it very slowly, reversibly, these two terms are identical, exactly equal in magnitude. Opposite in sign, they cancel, del S becomes 0. But if it is irreversible, then this term dominates. The chaos due to volume increase becomes more than the chaos due to temperature decrease. Decrease in chaos due to temperature decrease. The increase in chaos due to volume increase is more than the decrease in chaos due to temperature fall. So the net result is del S system will be greater than 0. So therefore I am writing this term will be superseding this term. This will be a negative term. There is a cooling in expansion. Same thing will happen in this term will be negative for compression, this term will be positive. So this term will be more than this term in irreversible process, the del S will be positive. So, therefore, I take a great charm in teaching thermodynamics, but when I teach from my experience and my association with the subject as a student, learning every day, please bear with me. In San Diego, in California, it is 2 minutes to 9, and it will be in India, it will be 2 minutes to 9:30. But in irreversible, let me finish. Steve, your network data is okay? Ritu, whatever you have missed, you can watch. I will take some time to upload. Okay? Steve, are you still there? Sib, are you there, Sib? Oh, yes. Sibdat is there. Okay. We'll be finishing by 9:30, I mean by 10, and my morning 9:30. But for irreversible, we shall be calculating. Since the temperature drop is not so high, it was 287 and that was 207. So this term will be dominated by volume term. The volume term will dominate the temperature term. So del S will be positive, is greater than 0. So this means the system, and I'm writing down because we have already explained second law in terms of entropy of the universe. So in this case, entropy of the surrounding SUR is also equal to 0. Both 0. In reversible, the surrounding is also 0 because no heat is exchanged. Surrounding में कुछ chaos बढ़ता नहीं कि घटता नहीं, लेकिन system में बढ़ता है. So in both the cases, in this case, del S universe is greater than 0 because of systems के लिए, and यहाँ del S universe is equal to 0. So we have applied this entropy change for all processes. Isothermal, isobaric, isochoirc, adiabatic, all processes. Then we shall be going into free energy now. Straight away we shall be, I'm showing you some of the things which I might have missed out. You can calculate, del S is the heat absorbed or evolved at a fixed temperature. That is a transition of phases, melting transition or vaporization. So if the molar heat of fusion is given 6 kilojoules per mole, then what is entropy change? You can just 6 into 10 to the power 3 joules per mole by temperature at 0 degree Celsius, because the melting equilibrium occurs only at 0 degree Celsius. So the increase in entropy is 21.96 joules per Kelvin per mole, because per mole is given here The data is per mole here. Therefore, this del S is an intensive property because it has stipulated the mass to per mole. But had it been as such, we have given enthalpy of fusion, not per mole, meaning any quantity, not defined. So then you would have no right to write per mole. Then it would have been an extensive property. Similarly, vaporization, heat of vaporization, molar heat of vaporization is this much at 100 degrees Celsius. So what is the entropy change? Entropy change is much larger during vaporization. The chaos, the disorder increases to a large extent. Now I have told you that whenever a gas component is involved, others are solids and liquids, there is a huge increase in entropy, del S positive. And if there is a decrease in complexity and molecular mass, propane, ethane, methane, if you compare between the three, more is the molecular mass, more is the entropy. And if the molecular mass are very close to each other, then more is the complexity. Propane containing 3 carbon chain, it is 1 carbon with 2 oxygen. Argon is a monoatomic, so the complexity decreases, means the entropy decreases. Even ammonia and helium. Ammonia is 17, this is 4. Undoubtedly, molecular mass wise, complexity wise, ammonia has more. So del S negative, the opposite, gas to liquid, liquid to solid, the chaos decreases. And there are 2 moles of gaseous component and there are 4 moles of gaseous components. So there is a decrease in number of moles of gas. Now, this is a very important question I have given. Somewhere you will find in your examination that 1 mole of helium gas at 10 K at 1 atmosphere pressure, compared with 1 mole of helium gas at 250 degrees Celsius and 0.2 atmosphere, which has got a greater entropy. For that, if the mass is fixed and component helium is fixed, in that case volume is important. You find out nRT by P. All the data are given. First ka nRT by P kitna, second ka nRT by P kitna. So if the volume is more, I have found that volume of the second case is more. So undoubtedly, even if it is 0.2 atmosphere, that makes the 2 has a greater entropy. Don't look to temperature alone. 10K, so 10K means minus 263. So it has got a lower entropy. That is okay. But sometimes you will be put into trap. You have to find out volume. If the mass is fixed, the component is fixed. I mean the chemical component is fixed. But in the second case, also 2 moles of nitrogen at this temperature and pressure, 3 moles of nitrogen, but here 3. So you have to take nRT per mole. That means you are using per mole or you have to use per mole nRT by P. So you have to find out nRT by P, more the volume, more is the entropy. Now, there are so many ways to express second law. Entropy of an isolated system or universe increases or remains the same in a spontaneous, irreversible natural process. The total entropy of an isolated system either increases or remains the same in any possible or happening process. It never ever decreases. It is impossible to convert all the heat drawn from a hot reservoir into work without transferring a part of it to the cold reservoir. Yes, one of the demerits, lacuna, drawbacks of first law, that it could not tell. It told about the conservation of energy. Total bank balance is equal to heat and work. Okay. But can all heat that your system is absorbing, can it convert to 100% work, expansion work, compression work? No. The answer is no. That comes from thermodynamics second law. That a part of it has to reject. It will take Q1 amount from the hot body, that is called source. Do out of Q1, some amount will be invested in doing expansion work, and the remaining amount, maybe small, has to be rejected. Our body also rejects heat through sweat. The second law is also applicable crudely in human system. First law we have already discussed. It is an isothermal system. Our body maintains the temperature at nearly 37 degrees Celsius. Isothermal, of course, open system. Doesn't matter, but temperature is maintained. and some energy is being wasted. I mean, not all food that you take that is used for doing work. Even if you do work, there will be some energy will be dissipated as heat through your sweat. So theta, that is another definition of second law, which we will study in cyclic process. Spontaneous change takes place in a direction that leads to more, and this is the initial, more disorderly, increase in the chaos, increase in the entropy of the total energy of the isolated system or universe. This is same as the first one. So we have already done this. This is spontaneous process. This is never happening. It's less than 0. But if it is 0, then it will happen, but equilibrium will come in the midpoint. So these examples we have already done. Then we are trying to go to the free energy change. I have already told you that when thermodynamics say no, it means no, and when it says yes, it means maybe. The kinetics plays a villain role that I have done. Free energy is a very important topic, which there is a lot of myth about del G. Free energy change. I will unravel the myth and clarify where is the reality that will come. So before that, I would like, this we have already done, isothermal process, individually we have done, but in the class now, I didn't take the individual method. Instead, I told the general derivation from here. This one we derived, and from this to this, the derivation is here. It's very simple. Pb is equal to nRT, divide Pb1 V1 by Pb P1 V1 is equal to nRT1, P2 V2 by nRT2. So divide V1 by V2 is equal to T1 by T2, and then you apply. In place of V2 by V1, you write this one, T2, this was V2 by V1, so it is voltage T2 by T1 into this P2 will come here, P1 will come here, so V1 by V2, so NCV T2 by T1 plus NR ln V2 by V1. So in place of V2 by V1, P2 will go here, P1 will come here, so it will be V2 by V1 is equal to this T2 by T1 into P1 by P2. So then what will happen? T2 by T1 will be taken as common. So here CV and here R, but CV plus R is equal to Cp. So we write Cp in its place. So now we have, just to have a similarity between P2 by P1, V2 by V1, I have exchanged P2 by P1 and put a minus sign. This is my style. Putting T2 by T1, P2 by P1 and putting a minus sign. So this is the second alternative definition of this one. Entropy change. Applicable, these two are applicable for all processes. For isothermal, this will vanish. For isochoirc, this will vanish. And for isobaric, this will vanish. And its corresponding Hamilton's law, Boyle's law, Charles' law will come. That we have already discussed. And for adiabatic process, this term will dominate over this term. This will be negative, this will be positive. Expansion के लिए, but compression के लिए, this will be positive, this will be negative. So they will be exactly compensating when this will be reversible, but it is irreversible. The positive term will be left out. So it will be, Ritu, you were there. So we will be, okay, but make sure that you, Siddharth, you watch the remaining part of the video. Okay, are you there still? You promise me that you will watch. If I don't send in the group, you can find in the Facebook. I will be uploading and you can get the first post will be the link of YouTube video, and you click it there in the Facebook itself. YouTube will open and you will get. Are you listening to me or you have already left? Ritu, are you there still? Who is there? Ritu, are you there? Okay. See if possibly you have left. And you have messaged me that you are leaving, so you must have left. कोई बात नहीं, we'll be winding. Free energy के बारे में हम बात करेंगे tomorrow. Yes, Ritu is watching, so we'll be solving a problem. So which Mr. Sibdat will watch the last part of the video. So this is, yes, these are the things. These are the two main expressions for del S, and then they are reduced to isothermal, isobaric, isochoirc, and adiabatic, reversible, del S system 0, and del S surrounding also 0. But for adiabatic irreversible, del S is positive, because the one term will dominate over the other, make del S positive. Then we shall be solving a problem, no doubt. These are simple data given. Isobaric process, isochoirc process you can use. But here, look to this equation. Calculate the change in entropy when 3 moles of an ideal diatomic gas is heated and compressed simultaneously from 300 K 1 bar to 400 K 5 bar. So temperature is increased. That means the pressure has also increased from 1 bar to 5 bar. टेम्परेचर इंक्रीज करेगा तो वॉल्यूम इंक्रीज करेगा. यूजुअली वॉल्यूम इंक्रीज करता है, क्योंकि चार्ल्स लॉ, अगर प्रेशर को हम छोड़ देते हैं किसी के केयर पर, फिक्स्ड प्रेशर पर रखते हैं तो. लेकिन यहां क्या होता है, यहां एक लड़का पिस्टन को दबाया है फ्रॉम 1 bar to 5 bar. At the same time, somebody else has heated from 300 K to 400 K. So both opposite things have happened. So pressure has not kept constant. So in such situation, you have to use both. That is why I told both. So where both are changing, I mean at least two things are changing, the others are also changing. If temperature and pressure are changing, volume is also changing. So in our equations, only two are required. So we have used temperature data and pressure data. किसी में है? The second one में है. NCP log T2 by T1 minus 2.303 NR. Yes, this one. I'm showing this one. Not visible, nahin. This part is not visible. I am saying this T2 by T1, and here it is written 2.33 NR P2 by P1, because both pressure data is given and temperature data. So I put them. N is 3 moles, and Cp, since it is a diatomic gas, there is no need for any data. 7 by 2 R, 7 by 2 into R, 8.3. Log 4 to 400 to 300, so 2 zeros cancelled, 4 by 3. Minus 2.303, 3 is written 3 here, again 3 moles. R is 8.3 here, not Cp, R. Log 5 by 1. Here is written 5 by 1 because it has gone from 1 bar to 5 bar. So 5 is the final pressure. Here written, you are not seeing that. So you are getting, the answer is 15 joules per Kelvin is the entropy change. That is an extensive property for the entire mass, for the entire 3 moles, not for 1 mole. Okay, so you have to look to that. Here also the same thing. Temperature and volume data are given. It's not an adiabatic process, but a person has done both the changes together. Not kept temperature constant, not kept volume constant. So pressure is also not constant. So volume data and temperature data are given. So you have to use this first one, which we have derived. Here it is NR and here it is CV. You know, the CV data is fortunately given. Okay, no problem. Otherwise, the gas is not named. If the CP data are not given, then the gas will be named as monoatomic or diatomic or polyatomic. Or it is oxygen O2 or it is helium. Then you can know approximately 3/2R is monoatomic for Cb, and so on. So here we had done, Ritu, a problem that in adiabatic irreversible process, you have to find the final temperature by using NCV delta T is equal to minus P external delta V. And expansion, the final temperature, though it is less than the initial temperature, it is a cooling, but it is more than the reversible process. It was 287 something. And in reversible, it came to 207. So the same type of problem here. So this is a question I have given. You can see that this is isobaric, 1 atmosphere. Then since the temperature is 400K, so this curve is isothermal. And then since temperature is changing from 400 to 350, volume is expanding, so it is adiabatic expansion. So you are asked to draw the diagram and find Q, W, del U, del H. So I have done, because this is isobaric, the work done will be minus P external into del V. So I have done it, which is NR delta T. If volume data is not given, then temperature data is given. So 400 minus 300 minus, so it is minus 830, because it is expanding. Isobarically, no doubt, but since it is expanding, the work will be negative work. And what? Q is equal to NCPDT for everything, NCPDT delta T. So N is 2.5 number of moles, 1 mole. No, 1 is not written, 1, and Cp is 5/2R because it is monoatomic. The Cp is 5/2R, and delta T temperature difference is going from 400, it is going from 300 to 400. I have not written the temperature conditions here. This is 300K. So for everything we have to use NCP delta T to find QP. So this is nothing but del H. This is nothing but QP is equal to del H. Immediately you write del H. But del U is equal to del H or QP plus P del V, not minus. In chemistry plus. So that is, but it is itself minus. So the internal energy increase is this much plus enthalpy increase is this much for first step. Second step is isothermal. The work done has a different formula, minus 2.303 nR T log V2 by V1. So this is 2V2. It has already told it is expanded 2 times. So 2 by 1, so it is log 2. So it is coming minus 2. And Q is equal to minus W. The sign will change. And for isothermal, del U is equal to 0, del H is equal to 0. And then third step is adiabatic. And adiabatic NCV delta T, del U is equal to NCV delta T. So it is cooling. 350 minus 400 is minus 50. So there is expansion work has to be negative. So this. And Q is equal to 0. Del H you have to find out, NCPDT. Del H has a meaning. Del H N is 1, Cp is 2.5 because it is monoatomic, into delta T is minus 50. So this will be how much? 75 minus 75 joules. N Cp, how many moles? 1 mole. And what is the temperature change? Cp is 2.5 R. I'm sorry. Oh, here we are missing one. I thought how it's so small. So whatever will be, that will be minus, you find out, you find out what is the enthalpy change in that adiabatic process. I told you, even if it is adiabatic, del H has a meaning. It is the net work output. Of course, del U is equal to W in a closed system, but some open insulated systems have a greater work which is performed by the system. So that del H has a meaning. So del H is equal to NCP dt once again. Only del H is equal to 0, I told you, in isothermal, in cyclic, free expansion, and Joule-Thomson effect, which we have not discussed yet. That is a first law thing which I have reserved for the last class. So with this, now see, contrary to a spring, normal iron or steel spring, in stretching of a rubber band, we sometimes we feel that stretching of a rubber band, the entropy should increase. No, entropy decreases, because in a rubber band the polymeric chains are entangled in a very messy state, so entropy is more. As we stretch, the polymer molecules, the macromolecules get straightened, and their interaction van der Waals force make them orderly. So during stretching, entropy decreases. The disorder decreases means entropy decreases, and it is exothermic. And when you release, unstretch it, again entropy increases. Similarly, boiling of an egg, what will happen? It is going from liquid to solid, so that entropy decrease, you will say no. Entropy increases, because inside the protein there are a lot of secondary, that you might be knowing more than us, that there will be secondary, tertiary, quaternary type of interactions, not the primary amide linkage. So on boiling, they had made the entropy small because of this large interaction. But when you boil it, all the secondary, tertiary, all these structures will be destroyed, and they will be free to have motion, chaos. So the chaos entropy increases during when we boil an egg. So that is what normally people think it is opposite. So I have explained them. Tomorrow we shall be doing Carnot cycle and free energy change. First free energy change concept, then Carnot cycle, and we'll see how idealized Carnot cycle is different from the internal combustion engine that is operating in cars. In petrol driven car, it is a spark which is needed. Spark which is needed for the power stroke. There are 4 strokes. The internal combustion engine that our petrol driven car or diesel driven car that you see, they are not like electric car which runs in electricity. It is converting same heat principle, but it is an open system, not the Carnot cycle, which is an idealized system to give you the ideal amount of work output or efficiency. So our car has 4 steps, but they are not a cyclic operation. It is a mechanical cycle, but not a thermodynamic cycle. There is a combustion inside, there is a continuous intake of petrol or diesel, continuous outlet of the exhaust gases. Such a thing doesn't happen in Carnot cycle. We'll be doing that, and I will sum up tomorrow. Then we'll go to the problems. Third law is not that difficult. We'll be taking up this problem together and then find entropy change. Since we have already discussed entropy change formula, we will be using them not only to find del H, del U, Q, W, but also del S. And also in the cyclic process, also in some reversible process, it will be 0. In reversible cyclic process, del S is equal to 0. System and surrounding. But irreversible, it is not 0. Sometimes system increases, surrounding 0. And sometimes system decreases, surrounding increases more than the decrease. So the net entropy of the universe increases. So that we will sum up. Tomorrow we shall be, tomorrow will be the 4th day. We'll be completing and going to thermochemistry and harder problems. And I will show you that I will be sharing this one. I'm sorry. This one. This NEET 2026. Tomorrow I will share. Many of them you can do. So easy. Delta G is relating, which we'll study tomorrow. Under isothermal issue, this one. Under isothermal condition, a gas at 300 K expands from 1 liter to 0.25 liter against constant pressure 2 bar. The work done by the gas, so simple. Minus P external into del V, 0.25 minus 0.1. So it will be negative work, expansion, negative work. So there will be 4 choices. 1 bar into liter is equal to exactly 100 joules. 1 liter atmosphere is equal to 101.3, but 1 is given. 1 liter bar is equal to 100 joules. So you convert to joules and get all the 4. I have not. So these things will be very, very easy for you. A gas is allowed to expand in an insulated container. That means it is adiabatic against a constant external pressure. Again, minus P external into del V from initial volume ethic to ethic. The change in internal energy of the gas is equal to NCV delta T. For any process, it's NCV delta T, but temperature is not given. So you have to use this formula. Minus P external into 4.5 minus 2.5. That will be equal to NCV dt. So we don't bother about NCV delta T. Delta T is not known to us. So that only liter atmosphere milega. So if you can make the conversion, 1 liter atmosphere is equal to 101.3 joules, then you can approximately you can get. This is an approximation to the nearest 5. But this is not approximation, but this I think answer will be I think this one or this one. Not 500, it will be either plus or minus will be known, but this, not this one of them you can find. So you can do after completing tomorrow's class, you can solve any harder problem or simple problem in thermodynamics. So with this, I conclude today's session. And Ritu, you have not watched for a longer time, so I will be putting the video in some time in YouTube. It will take some time. So you sleep today. Tomorrow morning, your first job is to take your copy and start watching and writing until you have, or sometimes you can watch till end, because remaining from the middle or from the last part, it is difficult to understand. You might not have understood some portion which has been connected with the first one. So you watch all. Thank you. So I am signing out. So I am not able to end live. मुझे दिखा नहीं रहा है कहाँ मैं ऐसे कर दिया. So will it automatically, कहाँ मैं ऐसे